Hello, this is lab report number 3 by group 4. So in this experiment, we explored how voltage, current, and resistance are connected by using a voltage current sensor. Our main goal was to see how resistors behave when arranged in a series, in parallel, and in a mixed circuit. So in the foundation of this lab is Ohm's law. That's basically the idea that the voltage equals current times resistance, or V equals IR. When you plot voltage against current, the slope of the line gives you the resistance, and using that concept, we got the data, graphed it in Capstone, and used the slope to basically calculate the experimental resistance values to compare with our theoretical ones from the color band on each of the resistors. So we started by testing individual resistors, then combined them in a series and parallel to see how total resistance changes essentially. And finally, we built a mixed setup, the two resistors in a parallel and one in series, to see how combining both types of connections affects the overall resistance. So you can think of this in everyday electronics, for example, like the wiring in your car or your house or even your phone, lights, outlets connected in a parallel but still working independently, while others are connected in series and they depend on each other. So this experiment helped us to visualize those ideas, but on a smaller scale. So overall, the lab reinforced how series circuits increase the total resistance and parallel circuits lower it, and it gave us a hands-on way to see and confirm Ohm's law and understand how real electrical systems are designed to kind of balance our safety efficiently and overall performance.
For our hypothesis, since we are calculating resistances, the questions we wish to debunk or answer is if the order of the resistors matter when it comes to overall resistance, and how the data will compare when the two mentioned configurations of the resistors are different. All right, so what is a resistor? A resistor is components that allow and control electric currents flow within circuits. This is important to know because in both of our hypotheses, we are inferring how the different setup of resistors will affect the flow of the current, additionally affecting the resistance that we're trying to measure. As you can see on the top right are the two configurations we're testing, A being the in parallel and B being the in series. And on the bottom, you can see that we have replicated both of these and even combining them in the bottom left corner in order to test it if it inhibits or increases the flow of the current. So to do this, the materials we used were 3 resistors in total, wires to connect them to the interface, and lastly, we used the Capstone software to log our data on a graph.
And now I'll talk about the procedures used for this experiment. So for step 1, measuring individual resistors, we began by connecting one resistor at a time in series with the current sensor and the signal generator, and in parallel with the voltage sensor. So the signal generator was initially set to 0 volts, and voltage was increased in 1 volt increments up to 10 volts. And for each step, current and voltage readings were recorded. And using the linear fit function in the Capstone software, we determine the slope of the voltage versus current graph, which represents the resistance of the resistor according to Ohm's law. And these measured values were compared to the theoretical values determined from the resistor color codes. And the percent error was calculated. And moving on to step 2. So next we discussed which configuration and series or parallel we would use and would result in a larger overall resistance. So setup A represented all resistors connected in parallel, and setup B represented all resistors connected in series. Based on theory, we predicted that the series connection would have the greater total resistance, while the parallel connection would have the smaller equivalent resistance. So step 3, we calculated the theoretical equivalent resistance for both configurations using the following equations. So we used the parallel and then the series. And these theoretical results were recorded in our table shown in the data section, which is later. And moving on to step 4, we then built the two circuits, first in parallel, then in series, and repeated the measurement process using the Capstone software again. We obtained voltage versus current graphs and determined the slope for each configuration. The slopes provided the experimental equivalent resistance values for both setups. Percent error was calculated between experimental and theoretical values for each configuration. And for step 5, after gathering data, we analyzed whether the order of resistors affects the overall resistance in both series and parallel circuits. And according to theory, the order should not change the total resistance. We discussed and justified this reasoning in our conclusions and comparing it with our experimental results. In step 6, next we connected two resistors in parallel and added a third one in series with the parallel set. This was done 3 times, changing which resistor was placed in each series each time. For every setup, we measured the overall resistance using the same voltage current slope method and recorded the results in the table. And this allowed us to analyze how adding a resistor in series affects total resistance. And finally, in step 7, we compared all theoretical and experimental results, discussing possible sources of errors such as connection resistance, sensor calibration, or inconsistent voltage steps. And we confirmed that our results followed Ohm's law and theoretical expectations with minor deviation explained by measurement.
The data that was acquired for this lab aims to measure Ohm's law and how we can assess the resistivity of the resistors. To do so, we utilized a program that calculates this in organized graphical representations as voltage versus current. First, we acquired our theoretical values of each resistor, which were chosen at random. Afterwards, utilizing the software, we tested for resistivity to obtain the experimental value of all 3 resistors. When we look at the graphical representations, the current lies on the x-axis while the voltage lies on the y-axis. As we observe each graph, the slope that is depicted represents our value of R for resistance. When we look at the graphs, we can see that the slope for resistor 3 is much steeper when compared to resistor 2 and 1. While resistor 2 is the closest to 0, this indicates that the current is decreasing and the voltage is increasing. And for the case of resistor 3, we can see the opposite, where the slope represents the decrease in voltage and the increase in current, which is therefore indicative of a higher resistance. For the second phase of our assessment, we want to evaluate whether resistors in either parallel or series connection. Observing what was captured, we can see that the parallel had the steepest slope out of the 3 separate resistors that were organized in series connection. Each was specified as the resistor in the serial position, while the other 2 remained in parallel. Interestingly, resistor 2 and resistor 3, when in the serial position, which was the one that was not aligned in parallel, have less current and higher voltage due to the slope being closer to 0. However, in parallel, the parallel displays a steeper slope, which is indicative of what we've seen in our last slide. As the current is increasing, the voltage is decreasing, which then conveys a higher resistance.
Voltage versus current graphs. By applying Ohm's law and interpreting the linear relationship between voltage and current, we were able to determine the total resistance in each circuit configuration. The results demonstrated that series circuits have higher total resistance as the resistances add together, while parallel circuits show lower total resistance due to the reciprocal nature of their configuration. This experiment not only reinforced the principles of electric circuits, but also highlighted the practical application of algebra and linear equations in analyzing physical systems.